Sidewalk Toronto Fellows. So if you're interested in smart cities, data science, or encouraging women in STEM and allyship, also interested in talking about those topics. I have a background in mathematics, pure and applied, and I took a course on calculus on manifolds once, out of the Spivak textbook, if you're familiar with it. And so it's a course on differential geometry. And that's what we try to use here to formalize the theory behind neural networks into something that has mathematical backing. So today we're going to talk about some of the concepts from differential geometry in terms of neural networks, which most of you would be familiar with. And this paper was actually covered in a NIPS talk last year, so if you're interested in knowing more, you should go listen to that. And so the first thing that I'll touch on is why it's important and why we should care. And I don't know about your data science work, but what I often find in my day-to-day is that a lot of what we do is very empirical. You come up with things that work, and you might have a good understanding of why, but not always. And so what often happens, I notice, is that people end up putting their understanding of the world to their data science, and you end up telling stories, which is not always bad, but not necessarily always correct either. And so what we hope to do, and this is a bit of an emerging research field, is to formalize some of what we know about neural networks in terms of mathematical theory, and we try to do that a little bit today. So what we usually think about in terms of neural networks is how do I extract what we call latent variables. So what do we not know about our underlying data, and how do we parse out variables or features that we learn with these neural networks to have an understanding of our different target classes. And so with a convolutional neural network, for example, we often explain them to people as learning layer-wise hierarchical representations of images that we feed it. With RNNs, or long short-term memory machines, what we do is we say that there are these cells that take care of your short and long-term conflicts and dependencies. And so that's kind of how we view things today. What we try to do in the context of this talk is to actually look at a geometric representation for deep learning. And what that means is that we try to formalize it in terms of space and transformations which act on space. And so the goal that we're going to frame a neural network as having is to learn an optimal, what we call coordinate representation system of the data manifold, where your different target classes are then linearly separable by hyperplanes. So you can kind of think of the concept of SVMs, where you're looking to be able to separate your target classes in this very intuitive way. And so what we're going to talk about today is this process of iteratively transforming your coordinate representations, which is the layers of your neural network, on top of your data manifold, which is your input data, by taking nonlinear transformations, so those being activation functions, which you're familiar with. And we're going to use all of that to turn it into a representation where the classes are separable. And this is kind of a visual representation of how we hope to do that. For the input data here, the classes are identified by the different colors, and you can see the way that we look to change the representation of our data as it moves through the different layers of the neural network. And so what we hope to find is that once you've trained a neural network and it is good at what it does, then your Euclidean distance, so that's the familiar concept of distance in regular space. So if you think like X, Y, Z space, you want to see that the input points of the same class could potentially be far apart in your original coordinate representation, because there are things that you don't know But then after you've transformed them accordingly with your neural network, you find that they are actually close together in your output coordinate representation. And that's kind of this image down here, where you have input coordinates that are all over the place. But once you feed them through a classifier, it's very clear that they are distinct. And in converse, 2 points from different classes could be close in Euclidean distance, but if you find a good representation, you'll find that they're actually far apart in the output. So there are a few definitions that we have to go through before we can dive into the geometry. So we'll talk a little bit about space. And so the question to keep in the back of your mind here is, what's a manifold? And so we start by defining what we call a topological space. So really all that is a set of points, and you can think of those as familiar to your Cartesian representation, each with a set of neighborhoods. So down here, this set right here is your neighborhood for some point P, where P is just, P is fairly arbitrary. But the neighborhood of a point is a bunch of other points that contain your point in question. And you can move along in any direction within that dotted boundary away from that point without leaving the set. So that's a neighborhood. It's just this area around a point in space. And so then we say, given a topological space and some point in that space, there's these things called neighborhoods. So you can think of that intuitively. Now, what's a manifold? A manifold is one of these spaces where we say locally it's equivalent to Euclidean space at each point. And what that means, the concept of equivalence actually is really interesting. We express that in terms of these coordinate functions. And if you're familiar with manifold calculus, there's this concept of a chart, which is really just a function, a collection of functions really, which map from your manifold over to familiar space, so R, which is very intuitive. That's something familiar, that's something that we know. So you're always looking to say, how close are we to real life space? Because when you have real life space, you have familiar concepts such as distance. You can say how far are things from each other, and you can apply some geometry in real life space. And the example that I like to use here is that the Earth is a manifold, and if you stand on it and look around, it's flat. And that is what we mean by it is resembling Euclidean space at any given point, because we know that the Earth is not flat. But if you zoom in close enough, it kind of looks like it is. So you can say, what is the distance from here to there?
Can I ask something?
Yeah.
So I didn't quite get the difference between CI and C. So manifold is an abstract concept, and C is the mapping between that concept and real space.
Mm-hmm. It's a bunch of functions which help you to map between the manifold and real space.
One of them, C is all of them.
So what is C?
So what is real space?
Real space is Euclidean space.
So I think it's CI for I goes from 1 to n.
CI is just part of the function C, because it's mapping to Rn. So for each R you have a function.
I see. So C is the family of maps, and CI is one of them essentially?
Yes.
No? Somebody said no.
CI is a projection from M to R. C is just the ones associated to one of the charts.
And you have a collection.
Yes, you have a collection.
Okay.
So the takeaway there being that you can find some way to find to map things close to Euclidean space. So some examples that you might be familiar with, one-dimensional manifolds are things like lines and circles. Two-dimensional manifolds are the plane, the sphere, and the donut. And three-dimensional manifolds are things like the Earth, for example. And there's this concept of embedding, where we can fit some structure into other structure where it is contained. And so that's all we mean. We can embed any of these manifolds into higher dimensional spaces. So you can contain lines in the Earth. Yes?
This might be a stupid question, but is a manifold allowed to have like boundaries and endpoints? So like a line with two endpoints, is that still a manifold by definition? Or does it have to be an infinite one? I actually don't know. It's okay if you don't know. I just
So you can choose either one, but like in this paper, they will assume that it's an infinite one.
got it. Okay.
Yeah, so in these contexts, you need them to be infinite.
Okay.
Yeah.
Okay, so a ball then would not be a three-dimensional manifold.
Sorry. Not infinite, but without boundary.
Without
Right.
boundary.
Yes.
Oh, in other words, it's
Yes.
like it's open, like okay.
You can always walk around. Like in a ball, you can always walk. You don't hit a wall. Like if you have like a half of a,
But if
sorry,
a ball is a three-dimensional manifold, you can walk, right?
Basically, no flat Earth here.
Yeah.
no, like if you're in a, oh, you mean like the ball, the solid
Yeah.
ball? Yeah, that's like.
Yeah, no big deal. Sorry.
So now that we have these structures, we dive a little bit into the maps between them. So a homeomorphism is one of these maps. And so we define it as a continuous function between two spaces where the inverse is also continuous. So if you can get from one place to another, there exists also an inverse for this function. And if you can get between one space to another space with this homeomorphism, then we call the two spaces homeomorphic. And we view them as what we loosely call the same. And so the joke that is often made in topology is that your torus over there on the left-hand side is the same as a copycat, because you can get from one to another without ever breaking the structure. So that's all it means for something to be homeomorphic. And so what we aim to do is take this manifold and look at it to be locally homeomorphic to Euclidean space. So every point has some kind of neighborhood or some patch where it is homeomorphic to some point, some patch in Euclidean space, even though if you look at the structure as a whole, it very well may not be. So hold this thought, because we'll get a little bit more to homeomorphisms in a second.
So what's the role of the inverse?
What is the role
In
of
the upper definition here, you have continuous inverse function. What's the role of it?
I guess if you were to frame it intuitively, if you want to view two things as being the same, you have to be able to get from one thing to the other and the other to back to the original thing. So you do need this concept of this inverse traverse between the two spaces.
So can you go continuously in one direction and not continuously in the other?
A function that did that between two spaces is possible, but it doesn't have the structure that we need to be able to use it. I wanted to first, before we get too deep into this, also frame this in terms of something which might be kind of familiar. So the concept of PCA, or principal components analysis. You might have heard people refer to this in terms of manifolds as well. And so I want to talk a little bit about this quickly. But basically, if you've got some kind of data manifold with PCA, because it's a linear dimensionality reduction technique, what you find is that you can possibly have projections onto your resulting components where it may not perfectly separate the data, and then you know that it calls for a nonlinear dimensionality reduction technique instead. So once you conduct PCA on something, what you find is that only some points on that space are now attainable because you've reduced what is possible. So this, what we call embedded subspace, is just a linear subspace. And here, if it's like the hyperplane, for example, it is also a manifold. And you can also, for some nonlinear dimensionality reduction techniques, which we'll get into in a second, have subspaces that might not be linear. But just wanted to frame that in terms of PCA, and then do a comparison between some non-linear dimensionality reduction techniques, like what we call locally linear embedding, or LLEs. And there's a whole field of study just in that, in nonlinear dimensionality reduction. So something called LLE and also isomap are two formulations of that. And basically they look to preserve the structure of your data while projecting them down to lower dimensional space. And so here, what you have in the top left corner is the original data representation. If you were to apply PCA on this, you would come up with something that doesn't well separate the classes, as you can see here. You've got them laid all over the place. If you take a look at some nonlinear dimensionality reduction techniques, you can actually get something that looks like this. So things actually get separated pretty well. And that's really all it is. You take higher dimensional space, you reduce it down into lower dimensional space, assuming that you can find some kind of representation for that higher dimensional data on some kind of non-linear manifold. And what we do with locally linear embeddings, the whole implementation of this being out of scope of this talk, but what it basically does is it finds this nearest neighbor representation for any point, and then expresses it in terms of a linear combination of those points, and it assigns some weights. And what we do here, which is kind of interesting actually, is that you freeze these weights, and then you look to optimize, so that's what this cost function here is doing. You freeze these weights, W, and then you look to actually find a better coordinate representation, which is interesting because we usually think about learning weights and keeping your coordinates the same. But here, what we actually do is we freeze the weights and look to find new coordinates. And that kind of ties into what we look to do with neural networks. So you look to find new coordinate representations. And that's the concept of locally linear embeddings. And the way that, yes?
I guess I missed half, like, why are we talking about weights now? I missed that one.
This is specifically related just to the concept of a locally linear embedding,
Okay.
which is another way of kind of changing your coordinate representation. And the theme here being that we're going to change coordinate representation. And it's kind of cool, the way that you solve, the way that you solve for this right here is actually to find the canonical representation of your matrix, so you get the eigenvalues and the eigenvectors.
Sorry? How is this related to the xi? I mean, you have the xi, you're getting your y.
So yi is your representation in lower dimensional space, and xi is the original space, the higher dimensional space.
And to get the y, this cost function is to get...
To get y.
How is it related to the x?
Each point takes line.
This is like a weighted multidimensional scale.
Is that wij xj or yj Danny is proposing?
Oh. You're looking to find y in the representation output. So is the question then, like, should you substitute in x here instead?
I'm just asking, is that supposed to be an xj or is it supposed to be a yj?
I don't think it's supposed to be xj actually. Yeah.
So where is the information about x then?
X is your original representation. So you can think of it as the original coordinate representation. So you would start with some kind of data manifold that has a bunch of X.
So could we just think?
So question, how do you constrain the Wij's? Because, you know, it's an overdetermined problem. Like, what constitutes a best linear combination of behaviors to approximate mean? If you want to do this?
Well, how do you usually find a representation for k nearest neighbors?
No, there's like infinitely many representations. How do you choose one?
I'm not. That's a good question. I'm not sure what the implication is if you choose a slightly worse one, actually. Yeah. So I see what you're saying. If you have because there are multiple ways to represent your points in terms of linear combinations. If you use a worse representation, how does this affect your cost?
What is like the canonical representation?
I'm not sure that there is a canonical version. I'm also not sure what the downstream effects of it are. But it's a good question. I don't know. Okay, so that's a really quick overview though of dimensionality reduction, and the theme being here, don't forget that we are looking to transform coordinate representations. That's all we're looking to do. So basically, what we're going to do here is take neural networks and do a similar thing. We're going to formalize neural networks as coordinate representations, and then you look to understand how close your points are to each other. So the key point right here is this last one. Your coordinate representation of what we call the metric tensor, which is a familiar concept in differential geometry, that is going to be formulated as what we usually know to be the loss for a neural network. And then we can also formulate this backpropagation process in terms of another differential geometry concept called the pullback metric. And you basically look to go backwards from your output and then propagate the error through in a very similar way. And the reason why it's interesting is because there already exist these concepts which are very well studied in differential geometry. So one more word on homeomorphisms. We talked about them a little bit as continuous maps between these two spaces. They're continuous one-to-one on CU and has that continuous inverse that you mentioned. And this is a very hand-wavy definition, but they preserve topological integrity. So you don't introduce any new aspects to your space after this transformation. It keeps it the same. And so what we're going to do here now is take a look at it in the context of a feed-forward neural network. So you have a homeomorphism as some kind of coordinate system, and you've got your data manifold, which we're going to refer to as M. And so what we do here is we take this homeomorphism as a coordinate system, as I'm going to refer to it as, and you represent it this way. So it just maps from your original data manifold to some, this is the formal definition really, some transformation on top of it, and that is contained in this R, so the real space with a dimension at the same as the dimension of your manifold. And we say that a feed-forward neural network learns coordinate representations as this phi here is going to be the representation of a layer in the neural network. And so we take a look at how it acts on your data manifold, and then we map it to, you can think of it as function composition, which is a familiar concept. You just take your layer map and you act on your previous representation, which is supposed to represent your data manifold. And then the way that we originally initialized this is through Cartesian coordinates, so something that's very familiar for our representation. So that's all this is saying. And then this is an iterative process, as we're familiar with in neural networks. So for the next layer, so this L+1 represents the next coordinate representation. You get that by taking the layer, so this layer phi, acting on your previous coordinate representation for m, and then that just maps it to your next representation. So you can think of that just as if you were to say every layer of my neural network is a map. It's a transformation of some sort. And I'm going to iteratively apply that. That's all this is saying. And so what we look to do actually is take this data point, any data point in your manifold, so this is an arbitrary selection. You want to be able to represent that with respect to some coordinate system. And so for the coordinates in your next layer, you can always keep representing each of these points as a function of layer-wise composition. So this says your next coordinate representation for some point Q can be defined as the composition of your layers. So this is just feeding through the layers of your neural network, where each of these feeds is representing a different layer. So this says you've got like L layers that are acting on this coordinate transformation, which is representing a point Q out of your data manifold. And then each layer of the neural network is represented by some phi. Phi?
So is each of the phi's a homomorphic map? Is that the relationship to homomorphism that you were talking about before?
Yeah, so each of them will be a homeomorphism.
Right.
Yeah. Question?
So, by textbook definition of manifolds, the only constraint you have on the coordinate functions in a certain chart is that they have to be consistent in terms of continuity. So, if they overlap in their domain, like, they might actually give you different coordinates in your space. How would you kind of arbitrate there? Like, yeah.
Yeah, so the question talks about the textbook definition of a manifold and what happens if you've got functions that map between them where you can get multiple
new coordinates. Because if it's not flat, you're guaranteed to have that problem. Like, there's going to be somewhere in your domain that more than one coordinate function covers, and like they're going to be different numbers.
That's actually perfect. You lead into the concept of a bijection, and that's a one-to-one and onto mapping between two sets. And we require that each of your transformations is actually a bijection. So that guarantees you actually that you don't have this confusion between what maps where. So we do touch upon the concept. So this is a function that is one-to-one. So everything you see here maps to something else, but it's not onto because this point doesn't have a corresponding element in the domain. This here is onto because everything here can be mapped back to your domain, but it is not one-to-one. And I think this is the case that you're talking about. So this point C here is mapped to by two different points in your domain. So then there's confusion. So this is functions that look like this are not going to be useful to us. We have to have the case where they are both one-to-one and onto. Does that make sense?
Not necessarily. Like, homeomorphisms are like one-to-one and onto. But what I'm talking is, for example, if you're mapping a circle, like a circle is a one-dimensional manifold. But you can't map the entire circle in one map to a line. So you have to have like 4 quadrants or like 2 halves. So how do you reconcile? And they have to have an overlap. You can't have seams in your mapping. So whenever they meet, like one coordinate function meets the other coordinate function, you have to have some amount of overlap. At least like textbook definition. So over that overlap, you have two different coordinate functions. And then in the new embedded space, you do different numbers for the same point. So each of those functions is one-to-one and onto. But there's no way of arbitrating which one should be your on. Again, like without creating a seam somewhere. my question.
Doesn't the bijection criteria guarantee that on both sides you get the same value?
Not necessarily. It's just that the functions are continuous. So if you like one half of
No,
the
but like phi has to be homomorphic, right? Which
Yeah.
means that it has to have a continuous
Inverse.
transformation and inverse, right? So that, like what you're saying is that it would have a case that from one side you get one value, from the other side you get another value, right? That wouldn't happen though because of the definition.
not necessarily, it can actually happen. You know, if we had a board, I could actually like draw the thing, like it's the numbers would be different, the topology would be the same, but the numbers would be different.
Like, the topology of the circle is not the topology of the line. Right?
Exactly.
So like, I think that by the definition that is being used here, you would just not end up with a function that would map a circle to a line. Like, you just end up with a circle that's like squished or stretched out. You'd never like create a C because of the whole, because of the definition.
Why
I
definition?
think.
Yeah, that's a good point.
That's a good point.
I'll come back to this because it's a good point. We don't specifically address it here. Okay. So before we get into backpropagation, we want to finish formalizing this. So the last thing that we haven't talked about is activation functions. So for some activation function, which we'll just call f, it also can be represented in this format by this right here. So this just says that you are going to act on some coordinate representation at some layer, and then I want to quickly highlight that f represents your activation function in particular, and c represents the layer as a whole. So that's the difference if you're wondering what the difference is here. And so the way that you can think about this is that the next layer, so the L+1 layer coordinate system can just be iteratively defined as transformations on the previous system. And this is an attempt to have a visual representation of it. So M is your data manifold. You are feeding it through multiple coordinate representations, which is what each of these xi's are. And eventually you come out here, you've got this final representation that comes out of each of these layer-wise maps. And so that's this concept of moving through different coordinate transformations. We're about to get into actually the pullback metric, which is going to act on the coordinate representation of the metric tensor, and that's just the loss between from each of your layers. And we define the push forward and the pullback map in a second. But this is just an attempt to show you what that looks like. We also specifically look at an example in this paper for residual networks, so sequential models where you can skip connections between the layers. And people use that to avoid vanishing gradients, is my understanding. And this can also be formulated in terms of your coordinate representation here, where instead of just this, which is the previous feed-forward network, you've also got this additional bit here, where you're adding on part of the previous coordinate representation. The author also highlights that a residual network with ReLU activation here is piecewise linear, and the concept of piecewise linear is something to remember. The idea that, for example, here this is not linear, but if you look at it from 0 onward, it is linear. If you look at it from negative infinity to 0, it's also linear. And because it's piecewise, we can stick all these pieces together, and we find this global coordinate system representation at the end. So for residual networks, You stick all the pieces together. Is basically all this says. I guess the very last thing here is that last output layer. So this is all represented the same way. This is something that is probably very familiar to all of you. Nothing's really changed here. And then really, this last point is just that the probability that some point is from your, some point in your manifold is from whichever target class J is just expressed as this probability here, where you do the softmax on this very familiar representation. So that's all this is. The softmax is the same. What is cool and different is this concept of the metric tensor. This is really the key for everything. So we call this thing the metric tensor, and I'm going to refer to it as G. It is just a function. What it does is it takes the input of a couple of tangent vectors for some point at a manifold, and it produces some kind of real number. So you take two vectors and you act on it, and it produces a real number. And that might seem familiar because the dot product does the same thing. And so I guess one thing to clear up here is just a tangent vector is just literally a vector that is tangent to your manifold at some point on that manifold. I think there's a picture that I have somewhere that represents that later on. But basically all the metric tensor does is it generalizes a dot product for non-Euclidean space, which is what we're working in. And then, as you know with the dot product, you can find the angle and the distance between two vectors. And so now you have this concept of angle and distance between two vectors in non-Euclidean space as well, which is cool. And then you can understand the curve length on your manifold. So non-flat space also has this concept of distance. And so what we're going to specifically use here is a positive definite metric tensor, and all that means is that whatever output you get from your metric tensor function has to be positive, and that is critical because distance is positive. And so a manifold with a positive definite metric tensor is what we call the Riemannian manifold. And I guess we're 20 minutes in and we finally got to why it's Riemannian geometry. But all this is a metric space. And what that means is that you've got space that you can calculate distance on, which is really interesting because if you know how far things are from each other in space, you have an understanding of how they relate to each other. And so the metric tensor really is the derivative of the distance function is what it is. And this is for some kind of coordinate system, some coordinate basis. The metric tensor is really just a matrix with entries that transform covariantly, so they move along with changes to that coordinate system. So if you're familiar with linear algebra at all, you might be familiar with the concept of a change of basis. And all this really says is that you've got this this matrix where you can track the changes to your underlying basis vectors. And so what we...
Excuse me.
Yes?
Could you just go back 2 slides, please?
2 slides?
Yeah. So this is going to put it. Okay, and to the next one. So the distance function is, we have the distance function before we have the metric tensor. Like, we're getting the metric tensor by taking the derivative of the distance function, right? Or do we have the metric tensor before that? And it just happens to be the derivative.
The metric tensor kind of exists. Like, it doesn't exist after or before you do something. It exists independently.
Right. I guess I'm just trying to tease out the relationship between defining the metric space and defining the metric tensor?
So you have a metric space if you have a metric tensor. If you've got some space and you can define a metric tensor, then you have a metric space.
Cool.
So from some arbitrary alpha layer to the next layer, really all this equation says is that we are iterating through coordinate transformations. And that's what this notation here means. It means you start with this coordinate representation, you go to the next one layer-wise. And this is really just the definition of your metric tensor in terms of the different coordinate representations layer-wise. And then AB really is just points where you're going to calculate distance. So that's all this is really saying. The key part here is to understand this in terms of different coordinate representations, which is all this notation is. And then in the output coordinates, we've got this now, what we refer to in this hand-wavy way as a flattened
Can I ask
representation.
something?
Yes.
And that's sort of the backpropagation, because you're calculating the previous layer from the next layer?
Yeah, so really I guess if the key to backpropagation is this equation right here. You go from output layer to input layer, and then you iteratively go through and change the coordinate representation. And actually, we talked about this. Okay, yeah. So backpropagation here is really just this represents the sequence. So you're going to take all of these matrices, starting from your output layer all the way through to your input layer, to what we say backpropagate the coordinate representation of your metric tensor. And anytime I say metric tensor, you can sub in the word loss, where this is just representing your neural network. So your weights, your inputs, and your biases.
But I guess my confusion is, like, if you go back, because in that expression you're using G, which is the metric tensor. So essentially what you're saying there is that you assume what the metric tensor is on, let's say, the last layer, and you're trying to figure out what it is for previous layers?
Yeah, so you have the metric tensor at the very end, at the output, and you go backwards through to find the previous representation. So I guess that's why this is an L+1. You define it in terms of the layer ahead.
And the reason that you're doing that is that you want your last metric tensor to have certain properties. So you set that, and then you. Okay.
Yeah, exactly. So you're looking for an optimal coordinate representation. Okay. I guess that kind of takes us here. So that's exactly what this tries to do. You have this output metric, and then remember, because we are likening ourselves to Euclidean space here, we calculate the Euclidean distance. And so all this says here is that for some layer, you can take the Euclidean distance and have the representations for each of these coordinate representations. For any coordinate space. And so this is kind of the result here. The intuitive way to think about this is, if you're familiar at all with the concept of an epsilon delta relationship or an epsilon delta proof, all this does is for some layer in your neural network, you take the delta neighborhood from one layer, and it maps it to the epsilon neighborhood in your next layer. And the metric that you're going to use here is Euclidean distance, because you have a Riemannian manifold. So this here says that these kind of form this epsilon delta relationship over the layers, and they tried to kind of illustrate this here. I'm not sure if this is helpful, but your original data essentially is these spirals, and you're feeding it through the layers of this neural network, and you look to kind of untangle them. Yes?
So, sorry, eta AB is the Euclidean distance between 1 and 1.
Between your points in the output layer.
It's the metric tensor.
Eta AB is the metric tensor.
The Euclidean metric.
Oh, okay, got it.
What is the capital P?
What is
What is capital P?
PA.
Previous
down
slide.
to PBPL.
Yeah. Differential.
sorry, which are those?
So that's the definition right here.
Okay.
Oh, okay.
Yeah.
So we take a look at each of, so those are between each point here. Yes.
So A and B are like coordinate indices, or
Yeah. In your output.
okay.
Yeah. Okay. So that is going to help us define really the pullback metric. And I guess the thing to highlight here is that all this so far assumes layer-wise dimension to be the same, but if you built a neural network, you know that you often want to vary the number of nodes between layers. So the way that we take care of this actually is with the pullback metric. So you want to be able to map between spaces that don't always have the same dimensions. So the pullback metric takes care of that. We say that we define the dimension of the data manifold to be the dimension of the smallest layer of your neural network. Then all higher dimensional layers of your neural network actually are what we call immersion or embedding representations of this lower dimensional representation. So you can think of it as just you fit these representations within these larger representations. That's all it means to embed something. You fit this structure within something else. I guess the nuance here is that immersions are embeddings where the derivative is injective on the tangent space. So your manifold might have self-intersections. Yeah. So the tangent space here is this. This plane right here is the tangent space. And intuitively, for any point on your manifold, all it really means is that you have all of the vectors that could be tangent to that space at any given point. Like you could draw a line here, and it would be tangent to your manifold. Is really all this means. So it contains the directions in which you can tangentially pass through some points on your manifold. So we're going to take two manifolds, M and M, and then you're going to take a look at the layer map on them, and you are going to say that it is a smooth map. So remember we said that it had to be bijection, which is all smooth really means. And then you're going to say, let's take the two tangent spaces, so let's take one of these for each of these manifolds. So say really you've got two shapes that look like this, and you want to find a map between them. And so the push forward map is going to be defined as this, so that star is the push forward. And and you go between two tangent spaces for two different manifolds. And it just takes some element and then it acts on it. So this is really the definition right here. You have some kind of function, and you take the push forward map, and you're saying, how do I get from something in this space here, this tangent space here, over to this other tangent space, even though my two underlying manifolds are very different looking as in here. And so this phi here is what we call the push forward map. So it sends things from here over to here, is all that really means. People say it pushes the tangent vector forward, hence push forward map. This, if you're familiar with multidimensional calculus, is the total derivative, which, someone correct me if I get this wrong, is the partial derivative of each of your dimensions multiplied by the derivative of each of your dimensions in relation to your independent variable. So all that to say, this is this abstraction for your derivative in multi-dimensional space. And so we need the push forward map to actually draw what the pullback metric is. And so for a couple of Riemannian manifolds, M and N, so these are just manifolds with some kind of metric of distance on them, you can define this map between them, and it's smooth, and then you're going to say, I've got this push forward map between their tangent spaces. Now, we define the pullback metric in terms of these push forward maps, actually, where x and y are points actually within each of your tangent spaces. So this is the linear map from the space of one forms, and one forms are really just parts. So it's a vector space, but it's really just parts of your cotangent bundle, which is just all of the cotangent spaces from n to m. And remember, you are going from here, n, over to m. So that's what I've called the pullback. And so it brings you from your resulting coordinate representation to the previous one. So this is very familiar in that it is the mathematical abstraction, I guess, to backpropagation, where you're pulling your error back through to understand how far away you are from the ground shoot. Now,
Can I ask?
yeah,
So what is F?
what is
We go back.
here?
Sorry? Yes.
Okay, in this case, f is an arbitrary function. It's not the activation like we talked about earlier, because this image here is completely unrelated to the paper. It is just some arbitrary function. And so the reason why all this is so important in being able to change dimensions is because your activation functions are limited. So if you couldn't change the number of nodes in your layer, in your layers for your neural network, for example, you'd be very limited in what you could do. So being able to transform your coordinate systems really helps you to be able to find eventually this, what we call optimal coordinate system, and that is closely related to your concept of a manifold chart. So this charts really are just, how do I represent my manifold? And then the authors, what they find is that like higher dimensions make it easier to separate more complicated data, as you might imagine. And so they did some empirical results on this fake data here. They also have some experiments done on ImageNet, and we don't get into that here, but if you're interested, the paper does touch on it a little bit. Really, all they did here is they've got this original data, and they start off with this batch size of 300, and they want to say, how do we untangle these spirals from each other? So when you get to about here, you can see it's already starting to get kind of untangled. This is like layer 14, for example, and it's not too bad. And what they say is that these sets have been disconnected, and the data is untangled in some kind of what we say unintuitive way. So this shape right here that you get at the end is not like very clear what the representation is, and that means that you have a very complex representation of your underlying data. If you can distill it into something like this, where it's basically a line, that means that you have a very simple coordinate representation. And if the concept of coordinate representations is still kind of fuzzy, you can think about really in space, you can just transform between Cartesian and like polar coordinates, for example, or spherical coordinates, and it's a very similar kind of concept. Yes?
I just want to know, what do the metrics and its pullbacks look like in this case? How do they relate to the difference in the two?
I don't know that I have a visual representation for that.
Like, is the metric shrinking around these spirals, or are things in a spiral closer to each other, or?
This formula, the different things happen for different formulas. That's like the formula that shows is basically how, for each of the points, the local neighborhood is changing and adapting. So like you can think in here, like the darker colors, you just look at the pattern and, I don't know, I'm guessing this is shrinking here in some places and expanding in some others. But like this is, for every point there is a set of local transformation that is happening that you can track through all of each of them. That's why in the first images, you see like the net having a weird shape, because some of them is shrink, some of them expand.
I want to know how the metric corresponds to the shrink.
Those are the metrics. Because the metric is basically the local matrix associated that gives the concept of distance.
Yes.
Could you please explain, this means a more complex coordinate representation of the data manifold was learned. What exactly that means?
So, here you've got clear separation, so you were able to somehow identify the difference between the classes, but the way that you represent these coordinates in space is not it's not a straightforward map to say how do you get from one point to another. So you can imagine, like, if you want to represent something as a line, that's what we would say is a simple coordinate representation. But here, I don't know what it would take for you to represent a bunch of your inputs like this, but that's kind of what it means for it to be complex. You wouldn't be able to simply just say, oh, I know how each of these maps clearly to this shape.
So how does that manifest in practical applications with more complicated forms of data?
So the authors do say that sometimes more complicated representations can improve performance. The idea being that your underlying data is more complicated, so you need a more complicated coordinate system representation.
Also, if you look at the images, like they're linearly separable, right? So if you just run a logistic regression, logistic classifier on it, it's going to be a super easy task, right? Just then still draw the line.
Correct. But I thought the point was to understand the mapping in that individual complex structure. I thought that was the whole point of this page.
We want to optimize to find that representation. As for what that representation means, you could probably write an entire other paper on that.
Oh, okay.
This is another couple of examples on the same data actually, and that kind of comes to your point. So they say here they have this 10-layer. This C1 just means that it's differentiable or smooth map. Network struggles to separate the spirals. So by here you've got this very complex representation, but it's still kind of confused as to the boundary. Here they decided to add a lot more layers, and you find that you have a very simple, clear delineation. And this is even more layers, and it is even clearer of the delineation. So that kind of speaks to your concept of complexity of each of your coordinate representations or your neural network. So, in conclusion, what we're really saying is that you can begin to think of neural networks in terms of these coordinate transformations. So we start with Cartesian coordinates, and then you learn a sequence of nonlinear coordinate transformations. So you learn a bunch of layer-wise representations to find a coordinate representation. So this optimal representation of your data manifold, your underlying input data, which is an optimal representation. And what the authors say is that this representation tends to be flat, which means really that you have this very simple concept of distance. That is, however, a very experimental result, and I wouldn't say that we have any mathematical backing for that just yet. And then what this really means, the takeaway here, if you want to start thinking about neural networks in terms of transformations iteratively, is that in the forward pass through data, you begin with the Cartesian coordinates and you find this nonlinear coordinate representation, so that the classes of your output coordinates satisfy your cost function. So that's that metric tensor concept. And then in the backwards pass, so in that backpropagation process, you start with the Euclidean metric at the output. So you take a look at the distance between your points at the output layer, and you are going to backpropagate the coordinate representation of the metric tensor, or loss, back through the network, and then you find the original representation in your Cartesian coordinate. So these are very closely linked. You can go forward through the representation, you can optimize it going backwards, which is very familiar to us. And then really all this is saying that you can find some kind of representation between your input and output layer, your input and output data, sorry, with this layer-wise transformation. And if you are interested in this, it is, like I said, an emerging research field, and so there are some very big names in the field trying to push this idea of geometric deep learning. There's a TWIML talk on it, and there's an entire website by one of the key authors of one of these papers who goes much more in depth into it. So I'd recommend checking that out if you're interested in relating neural networks to manifold theory. If you're interested in locally and linear embeddings, which is that non-linear dimensionality reduction technique that we talked about, there's also a very good paper here that serves as one of the base papers for that research field. And then at NIPS a couple years ago, actually, some authors, including Ian LeCun, actually tried to talk about geometric deep learning in terms of non-Euclidean space. So it's a concept that is very early in its implementation and in its research maturity, but it's backed by some big needs, and it has a lot of promise, and it's kind of cool. So there you go. Thank you.